All right, we are now recording. So welcome to physics. I'm curious to know, does anybody know what special day today is? Today is
Earth Day.
Earth Day. Very good. Yes, today is Earth Day. So happy Earth Day, everybody. It's a beautiful, beautiful day outside. I hope after class you guys go outside and walk around and enjoy the incredible, amazing weather outside. Wow, so cool. Okay, before we get started, does anybody have any general questions about anything? I'll take that for a no. All right. Okay, let's jump right into the fun stuff. Okay, so the answers to the quiz that we took last time we met. All right, so if you're out on the ocean and you only want to talk to boats that are in your line of sight, you don't want to have people who are over the horizon talking to you, you want the very high frequencies. Because the reason is you do not want diffraction. You, yeah, okay, so we talked about this last time, so I don't think we need to elaborate. Okay, question number 2. Okay, so if you want to listen to 105.1 on the FM dial, so the first thing you need to know is the numbers on the FM dial, are they in megahertz or are they in kilohertz or some other thing? And it turns out FM is megahertz. Okay, very good, Hiram. Yep, you're right. Okay, so now we know that it's 105.1 megahertz. Okay, so then we need to know the frequency. So we take everybody's new favorite equation, lambda equals V over F, and we replace V with C. And we do a little bit of algebra to get F equals, or no, actually we don't need to do algebra, it's already in the right form. Okay, so we figure out what the wavelength is, and then what fraction of the wavelength do we want? 1/2. And now that's for a standard antenna, and I do need to warn you that when you guys get into, if you get into this really deep, you'll find out there are different designs for antennas. So this rule of thumb that the book gives where they say the ideal antenna length is half of the wavelength, that's only true if you're using the most commonly used type of antenna, but there are other types, so be careful about that. All right, so I get 1.4 meters is the length for that. Okay, oh, by the way, let's go back up here. So some of you are going to say, hey, wait a minute, 1.4 meters. I've got an FM radio, and I know that it does not have a 1.4 meter long antenna. So what's the deal? Well, the answer is that even if your antenna length is not the perfect ideal length, I mean, it'll still receive. And if you've got a really good amplifier in your radio, you'll be fine, even though your antenna length isn't the ideal. Okay, you'll still receive and you'll still be okay. It's just the 1.4 is going to be the ideal length. Okay, so dielectric constant is very similar to refractive index. They both are a measure of how much does the wave, the electromagnetic wave, slow down as it's going through the material. Okay, so make sure you understand the relationship. The refractive index is the square root of the dielectric constant. Make sure you know that. So 1.5 is the answer there. This is an answer that, or this is a question that I think is really important because I've heard so many people say, well, I read in a book that a wave is both a particle and a wave. And so they get the mistaken impression that it sometimes it changes from a wave to a particle. So, you know, they think that sometimes it's not a wave, sometimes it's a particle. And that's absolutely positively not the case. Light is always, always, always a wave. It's just not the kind of wave that people usually think of when they hear the word wave. It's not a continuous sine wave. It's actually just a little burst of a wave. So make sure you understand that. That's important. And finally, the secret word was pizza. Okay, so let's move on. Okay, so you guys, hopefully you're all aware that this Friday is a test. I don't know how you could possibly not be aware of that. And my standard policy does apply. Any quizzes that you want to retake or any late homework that you want to turn in must be done before 1 o'clock Friday afternoon. I do not accept late stuff. I mean, after the test, this, it's kind of pointless. So if you want to retake a quiz, you're welcome to do it. But you've got to email me and tell me that you've done it, because I do not have my my Aspire scores and my Canvas scores automatically linked like some teachers do. I've just heard too much trouble where there's been issues where things didn't sync up right, and so I just say, forget that. So you have to tell me, send me an email telling me that you've retaken a quiz. Now with homework, Canvas should notify me when somebody turns in a late homework assignment, but just to be safe, I would recommend that you also email me and tell me about the homework. Now, a surprisingly large number of you guys have used up all of your late passes. Maybe it's this whole school from home type thing. Maybe it's all a little bit overwhelming. But if you've used up your late passes, that's not good. We still got almost 1 whole month of school left. So watch out for that. Okay, now let's talk about Friday's test before we get into the practice test. Why do you need to use a late pass? Oh, hey, Joshua, you're right. You're right, Joshua. That's never been my policy that you need late passes to take quiz. Thank you. You are correct. Yeah. Okay, so for those of you who are watching the recorded version rather than the live version, the comments don't show up on the recorded version. So Joshua just typed in a comment saying, hey, wait a minute, why do you need to use a late pass to retake quizzes? That's never been the case before. And Joshua, you are right. Boy, it's been so long since I taught class the normal way, I've forgotten how the normal class works. Okay, so yes, so you don't need to worry about late passes if you're redoing a quiz. You can do that. But you still do need to worry about the timeline, okay? You still have to retake those quizzes before 1 o'clock on Friday. If you retake the quizzes after 1 o'clock, that will not be accepted. Okay, so thank you for reminding me of that. Okay, now let's talk about Friday's test. So you've got to understand this because it's a little awkward and it could be potentially confusing. If you've looked on Canvas, you'll see that I have already reserved space on Canvas for the test, and there's 2 separate assignments. The first assignment is the multiple choice questions. The second assignment is the free response, and you must do both parts in order to completely do the test. Now, the multiple choice part of the test is going to have the vast majority of the problems on it. I haven't completely decided everything, but the overwhelming majority of the questions on the test will be multiple choice. And then the free response part, I'm only going to put a few questions on there that are free response. Okay, now, I'm really worried that people might spend too much time on the multiple choice. So I have designed it so that it can be done in 45 minutes. How many questions are on it, you're asking? I haven't exactly finished the test yet, so I don't want to give you a number and then have you come back and say, hey, wait a minute, you told us this, and then it was actually this. Let's just say the majority of them will be multiple choice. And so I have put a time limit of 60 minutes on there. And I'm designing it so that it can easily be done in less than 60 minutes. Okay, so assuming that you start the test right at 1 o'clock, Canvas is going to note what time you started part 1. And it will give you 60 minutes from that time. And then once 60 minutes is up, Canvas will cut you off, okay? And so then, or hopefully before then, you'll move on to part 2, which is a separate Canvas assignment. And I didn't put a time limit in terms of number of minutes on that, but I did tell Canvas to cut it off at 3 o'clock. Now, 3 o'clock is actually a little bit longer because previously I had told you that I scheduled 90 minutes for the test. I decided to give you an extra 30 minutes. I'm still designing it so that 90 minutes should be enough time. Okay, I'm not intending it to take 2 hours, but I'm just giving you a little extra time just to be safe. Okay, so with the free response one, Those are going to be more difficult problems. Those are going to be problems where you might possibly make a silly mistake somewhere along the way that would cause you to get the wrong answer at the end, but you could deserve partial credit. And so, so what I'm going to have you do is, most of you seem to be very comfortable with doing your homework on paper and taking a photograph of it. The overwhelming majority of you, that's what you're doing on your homework. So that's a great way to do it. Just do them on the paper there, take a picture, upload it. A few of you have been typing your homework answers into the text box on Canvas. And if you want to do that, you can do that. Drawing pictures is going to be kind of difficult. But you could certainly type in your equations. If it was me, I would plan the first way. I would plan to do it on paper, draw your pictures out on paper, show all your work, and then upload it to Canvas. So Maddie's asking, which one should you do first? I would recommend that you do the multiple choice one first. I guess it doesn't really matter. But I would recommend do the multiple choice one first. The first several problems on the multiple choice are going to be really easy. I hope you think that they're going to be easy. So they're going to go really fast. There's going to be a couple problems on the multiple choice that are a little bit more difficult, not horribly so. So I would do the multiple choice one first. Okay, any questions about how the test is going to be run? Does everybody understand you must take the test between the hours of 1 o'clock and 3 o'clock? Okay, Canvas will not let you start sooner than 1 o'clock, and Canvas will not let you continue after 3 o'clock. Okay, so I don't see any more questions. So let me switch over to share a different screen with you. Okay, all right, so you should all now be seeing the practice test with my answers written on there. And I think what I'll do is I'll just go through in numerical order. Normally I go through part 2 first, but we should have plenty of time. So I'm going to go through just in regular numerical order. Okay, so question number 1. Okay, so if you have a wire, and you guys all know there's a magnetic field that goes around the wire, okay, and somewhere in the book that's not obvious, they tell you that the magnetic field falls off. It's inversely proportional to the distance from the wire. It's not like the things we're used to with gravity or with electric fields when we have a point charge. In those cases, it falls off as 1 over r squared. But if you have a wire, then the strength of the magnetic field falls off as 1 over r. Okay, so if you double the distance, then it's going to go to 1/2. Okay. All right, question number 2, if you double the current, well, that one you should definitely know that the strength of the magnetic field is directly proportional to the current, and it's not the current squared or anything, it's just proportional to the current. So that means if you double the current, it'll double the amount of the magnetic field. Okay, question number 3, you've got 2 small electrically charged particles, you double the distance. Well, in that case, the force falls off as 1 over r squared. Okay, so if you double the distance, it's not going to go down to 1/2, it's going to go down to 1/4 of what it used to be. All right, so there. Question number 4, have you doubled the speed that an electrically charged particle is moving through a magnetic field? Okay, again, the magnetic field in that case is proportional to the velocity squared, or no, proportional to the velocity by itself, not the velocity squared. So if you double the speed, you're going to double the amount of force. Okay, so I'm hoping you guys agree these are all really easy questions. Okay, so now here come the fun ones. We're going to do this is where I really regret not having class at school, because I always get such a kick out of watching students do the test, and they're sitting there, they're writing on the paper and they got their hand and they're doing the hand dance trying to figure out what direction things are going. It's entertaining to watch that, and I'm not going to have my normal entertainment here. Okay, so Yasmin, I see your question. Let me just finish my thought here and then I'll get to it. Okay, so question number 5 here. Okay, so we've got a particle that's moving to the east, and it's a positive particle, so we're going to use our right hand, and our thumb is going to be pointing in the direction that the particle is moving. And then our fingers are going to point in the direction that the magnetic field is pointing. Okay, so let's see, north, south, east, west. So that's east that way for me anyway. So my thumb needs to point east. Let's see. Okay, so oh, no, it's moving northward. So my thumb needs to point northward. Magnetic fields are pointing to the east. So that's going to be down. Okay. All right. Okay, so Yasin, you asked what equation could be used to represent number 1. Okay, so Yasin, I would just say write it as the B field, you know, B in the absolute value signs, and just use a proportional sign. And so the magnitude of the B field is proportional to 1 over R. That's the way that I would write it. Now, you guys know that, you know, if you want to replace that proportional sign with an equal sign, then you do have to put a constant in there. And I am not going to worry about what the value of that constant is in this class. When you guys take the University of Utah physics class, which I hope you all will, then you'll find out about the constant in that case. So for right now, don't write it as an equation, just write it as a proportional sign. Okay, so let's on number 6 now. So we got a particle in problem number 6, it has a negative charge. So what I do is instead of using my right hand, I use my left hand. Now, if you want, you could use your right hand and you could figure out what direction your palm is pointing, and then the answer would just be the opposite of that. But I find it's easier to just use my left hand. Okay, so negative charge, left hand. Charge is moving vertically upwards, so my thumb goes upward. Magnetic field lines are running from west to east, so for me it would be that way. And so my palm then is pointing to the south. Okay. All right, number 7, we got a wire that's oriented vertically, and the magnetic field lines are running vertically. And so hopefully you guys remember that the real equation has a sine theta in it. Okay, the real equation is, you know, whatever times sine theta. So if they're both vertical, the angle in between them is going to be 0, and the sine of 0 is 0. So number 7, there's no force at all. Now, some of you might say that's a trick question. I do not think it's a trick question. Okay, so I don't like putting trick questions on a real test. I love putting trick questions on the practice test. But on the real test, I don't put, I try not to put trick questions. But number 7, I do not consider that to be a trick question. So be prepared for something like that. Okay, number 8, we've got an electrical transformer. Okay, so we got 28 turns on the primary, 170 on the secondary. And so, so what I do then is I just take 170 divided by 28, and I see that that's a factor of 6.07, okay? And so then what that means is that the ratio of the turns has to be this, or the ratio of the voltage is going to be the same. Okay, so it works out to be 730 volts. So Milo is asking, will you get a copy of these answers? Do you guys want one? You like in a file? I mean, okay, well, okay, that's overwhelming, yes. Okay, okay, all right. I will take this file that you're looking at right now, and I will upload it to Canvas afterwards. Okay. Okay, number 9. Okay, now again, some of you are going to say number 9 is a trick question. I do not think it's a trick. Okay. So in this case, you need to know that transformers do not work with constant voltage. They only work if it's alternating voltage. So the answer to number 9 is there will be nothing on the output side. Okay, this is not a trick. Okay, all right, number 10. Okay, so again, something that some of you might consider to be a trick question. I say it's not. Okay, so if we got a radio wave, it doesn't matter what the frequency is. I just put that number in as a red herring, because I know that a lot of you guys, you work on the theory that, well, if Mr. Hendricks gave us the number in the problem statement, then he must expect us to use that number. No, I quite often will purposely throw in numbers that you are not going to use. So it does not matter what the frequency of that radio wave is. The only thing that matters is that it is an electromagnetic wave. all electromagnetic waves travel at the speed of light. Now you'll notice over here that I first wrote my answer as 3 times 10 to the 8th, and then I said, well, wait a minute, sig figs. So this number here had 4 sig figs in it, so I rewrote it as the speed of light with 4 sig figs. But I'm not worried about sig figs on this one. What I worry about is to recognize that the speed of light is the speed of all magnetic waves. Okay, so the cell phone compared to a television signal. Okay, so in the reference sheet that I gave you, it tells you what the wavelengths are for cell phones and television signals. And so if you look that up, you'll see the wavelength, or I'm sorry, it tells you the frequencies. Sorry about that. Okay, so if you look it up, you'll see that the frequency of a cell phone is higher. And you guys know that there's an inverse relationship between frequency and wavelength. So if the frequency is higher, that means the wavelength is smaller. Okay, so the equation for Coulomb's law, you had better know that. Here's where it's a shame that I can't give you a test where there's no cheat sheets allowed. This is something that you should have memorized. You should not need a cheat sheet for that. Same with the equation for electric force, and same with the equation for voltage. You should not need to look those up on a cheat sheet. Those should be burned into your memory cells. Okay, so electromagnetic radiation with a frequency of 10 to the 7th. I trust that you guys have the page in your book bookmarked. I warned you that you're going to need to look at that page. So that would be a great place to look to find this. You'll find that it's X-rays. Look on that same page. You'll find out that this is microwaves. Okay. Number 17, you got KUER radio on the FM dial. So you need to know FM is megahertz, AM is kilohertz. So you need to know that. So 90.1 megahertz works out to be 90.1 times 10 to the 6th. And seeing as how I told you to use scientific notation, you cannot leave it like this. You have to put it over like this. So I trust you're all good on that. I'm moving pretty quickly here. Is everybody okay with the speed that I'm going at? Do you want me to slow down, speed up, or so we're okay, we're good, all right. Okay, so here's KSL radio. It's on the AM dial, so that means it's kilohertz. So 1160 kilohertz, whereas 1160 times 10 to the 3rd, which is 1.160 times 10 to the 6th. Okay, now we get into the real questions. Okay, up until now, they should have been trivially easy. Now we're getting into one that's a little more interesting. Okay, so we got 2 parallel plates separated by a known distance, and we've got 9.1 volts on these plates. Okay, so we want to know the magnitude of the electric field. So hopefully you've either got it memorized or you've written it on your cheat sheet. And by the way, use a cheat sheet, please. Okay, even though you say, well, I got the whole book, I've got the whole internet, why would I need a cheat sheet? Well, because creating a cheat sheet is one of the best things that you can do to take a test. Even if you're not allowed to use a cheat sheet, I always would prepare a cheat sheet for every test I ever took. Even if I wasn't allowed to actually use the cheat sheet, just the act of preparing it makes you look through the information and figure out what's the most important and what's the least important. It's like, yes, Jaron is saying it's like organizing your room. Although, as some of you know, that my room tends not to be very organized. Okay, but I do like organizing the brain, that I do. Okay, all right, so hopefully you got this equation, which you then just rearrange, stick in the numbers, and you'll find out that the electric field is 360 newtons per coulomb, okay? And then, so you wanna know what is the force? Well, remember that the defining equation for electric field is force divided by the charge, okay? So even if you don't have a charge there, you can still have an electric field. So let's say you have an electric field and then you place a charge in that electric field. So the Q there is the Q of whatever charge you are placing in that electric field. So in this case, it's a proton. And so you guys need to know that the charge on a proton is the same as an electron, except it's positive rather than negative. But the numeric portion of it is exactly the same. So you plug in the numbers and 5.8 times 10 to the negative 17. Okay, now problem number 20. You do need to be a little careful on here. There's one area where I'm willing to bet a lot of you made the mistake here. So if you look at my picture here, you see I've got the B field going straight east, okay? And my velocity vector is 28 degrees east of north. Now, if you are not careful, you're going to take this equation, F equals QVB sine theta, and you might just plug in 28 for theta. But here's why you really need to draw pictures. Drawing a picture is one of the most important things you can do. If you draw the picture, you'll see that the 28 is not the angle in between the V and the B. The 28 is the angle up here. So the number that you plug in for sine theta here, that theta has to be the angle in between the V and the B. So you don't want to plug in 28, you want to plug in whatever 90 minus 28 is, which is in this case is 62. Okay, so if you didn't get the answer I got, I'm willing to bet that's probably what you did wrong. Okay, number 21. Okay, so we got a radio intended to be used at or around 50 megahertz. So we're going to solve this one exactly the same way that we did the quiz question, which we already talked about a few minutes ago. We need to figure out what is the wavelength of a 50 megahertz wave, which is given by this equation. And then we just take whatever that wavelength is and cut it in half, and that will tell you what the ideal wavelength is. Okay, so Anna, you're curious about it. Can you elaborate? What do you mean? What is it specifically that you're curious about? And Anna, if it's difficult to type in your question, just go ahead and hold down the space bar and then speak it. The direction for question number 20. Okay, let's go back and let's talk about it again. Okay, so this is the equation that I hope everybody agrees. Okay, so F equals QVB sine theta. The issue is, what do you plug in for theta? So this equation is derived or experimentally determined, assuming that theta is the angle in between the two vectors. We got the velocity vector and we got the B vector. This theta here has to be the angle that's in between them. So when I told you that the velocity vector was 28 degrees east of north, that means the velocity vector is this angle up here, which is not the one that we want. Okay. All right, so, okay, looks like that answered Anna's question. Now, Jaron is saying thumb points in the direction of the velocity. Okay, good. Okay, and fingers go in the direction of the E field. And so then the angle is the angle in between the two of them there, if that's things, but, or the magnetic field. Yeah, magnetic field in this case. Thank you. Okay, so let's move on. Number 22, unless I see any more questions. Okay, so this one, actually, I should have put this one up early in the test. This is one of the ones that I hope you guys agree is trivial. All you got to do is lambda equals C over F, and bingo, there's your answer. Okay, so hopefully you guys agree that one's good. Okay, 23 now. Okay, so we got two spheres. We know the charges on the spheres. We know the distance between the spheres. Be careful about the units. The distance is in centimeters. So if we're going to go plug it into Coulomb's law, it cannot be centimeters. We got to convert it into meters. Okay, and bingo, this just pops out. Now, you'll notice now this, everybody always asks me the question, and in fact, it looks like Annie, thank you, Annie, that is the question that everybody always asks. The question is, how do you know the direction? Okay, so what I do is I let the picture tell me the direction. So I look at the picture and I've got a positive charge here and I've got a negative charge here. Okay, so I know that they are going to repel each other. So I didn't actually do it here. Maybe I should do it. But in my mind, I draw an arrow here so that I know that this guy is going to get pushed to the right and this guy is going to get pushed to the left. Wait a minute. I think I made a mistake here. Okay, so let me make sure I read the question right. So what direction will it feel? It is the one on the left. Oh, wait a minute. Okay, no, okay. No, I didn't mess up. Okay, I thought I made a mistake, but I was wrong. Now you might say, well, that counts as a mistake. No. Okay, these guys are oppositely charged, so they're going to attract each other. Okay, so the guy on the left is going to feel a force that's pushing him to the right. The guy on the right is going to feel a force on the left. Okay, so yeah, what I put here is correct. Okay, so in answer to your question, Annie, I look at the picture and I let the picture tell me what direction the forces are. And then when I'm doing the numbers, I just leave out the pluses and minuses. And I just put in the absolute values because I've already determined the direction, and the minus only tells you the direction. Okay, so I hope we're good on that one. All right, so let's get into the more fun problems. Okay, number 24, just a conceptual question. But it's really important that you understand this. This is the reason why I put things in the order that I do. If you want to know what light is, if you want to really truly understand the nature of light, you have to understand electricity and magnetism, because that's what light is. Light is the interaction of electricity and magnetism. So that is why they are fundamental. Okay, AM and FM. I hand drew some pictures here. The pictures that I put in the video that I didn't draw those pictures myself. I downloaded those off the internet. I think those pictures do a better job of describing it. But basically, you've got a super high frequency radio wave, and what you're going to do is, if for AM, for amplitude modulation, you're just going to stick this wave on top of that, and basically the way you do that is you multiply the two signals together. Okay, and so right here where you want the sound wave to be high, you have high amplitude. Right here where you want the sound wave to be low, you have low amplitude. Okay, so you're modulating the amplitude. And so after people had broadcast radio that way for a long time, they found out that they were getting lots of noise. For normal talking, it didn't bother anybody. But if you're listening to music, the noise that you get, it bothered some people. They say this music quality isn't as good as it could be. So Milo is saying, ever listen to AM in a thunderstorm? No, I have not. Have you, Milo? But yeah, that would be an interesting case. Yeah, I'm sure that you would get some weird effects then. Okay, so for FM, what you do is you make it so that when you want the sound intensity to be high, you have the wave be right on the carrier frequency. And so that way the receiver is going to hear it nice and loud. And when you want the sound to be low, then rather than modifying the amplitude, what you do is you make it so the frequency is a little bit off from the carrier frequency. So it's not so far off that the radio can't pick it up, but it won't pick it up with the same intensity. So FM is less susceptible to noise. Okay. All right, number 26, this was one of the questions on the quiz, which we've already talked about. So I hope you guys understand there. So if you've got thousands of boats all out on the ocean at the same time, and they're all talking on the same frequency, if you've got diffraction, so that these waves carry over the horizon, you're gonna step on top of each other's conversations, and it's gonna be awkward. So high frequency is definitely better because you do not want diffraction in that case. Okay, all right, so here, this scan doesn't show it very well, but we've got the wire here. Well, I guess you guys can see it. So this wire is connected to the positive terminal of the battery. Okay, so I was depending on you guys to remember that the traditional current, the back before people knew that there was such a thing as an electron, people just they had to pick one option. So they knew that something was flowing. So they didn't know if it was flowing from the positive side to the negative side or whether it was the other way around. So they just kind of flipped a coin and they assumed that it's traveling from the positive side to the negative side. Now, later they discovered that there are these things called electrons, and they did some tests and they found out that actually they guessed wrong. What's really happening is the electrons are flowing the other way. But by then they had already they'd written all the textbooks and they'd done all the math equations, and nobody wanted to change them. So we still call it the traditional current. We treat it as if it's positive charges going from the positive side to the negative side, even though we now know it's actually different. And so when we use the right-hand rule, we have our thumb point in the direction that the positive current would be flowing if that was what was flowing. Okay, so our fingers are going to be curling like this. And so hopefully you guys realize that if you curl your fingers properly, then up above the wire, your fingers are going to be coming out of the board towards you. Down below the wire, your fingers are going to be going into the board or into the paper. And if you're in front of the wire, your fingers are going to be going down. And if you're behind the wire, your fingers are going to be going up. So Jaren's saying, I can't believe you messed this one up. It's so easy to mess up. It's very, very easy. So you gotta go through step by step by step. Okay, number 28 was the hardest problem on the test, for sure. And I did not give you anywhere near enough space to do that. So I've done it on a separate sheet of paper, which here it is. So here's the paper. So are the circles supposed to represent positive and negative? Okay, so this is something that everybody needs to know. This is really important. Let me see if I can, okay, zoom up on it. Okay, a circle with a dot in it. That is intended to represent an arrow that is coming right straight at you. And that dot in the middle is the pointy part of the arrowhead coming right straight at you. Okay, so a circle with a dot in it means it's coming towards you. A circle with a cross in it, that's intended to represent the back side of the arrow as the arrow flies away from you. And on the back of the arrow, there's some tail feathers. So those crosses are intended to be the tail feathers of the arrow as it flies away from you. Does that answer your question, Amina? Okay, if I don't see otherwise, I'm going to assume that it does. Okay, good, it does. All right. Okay, so let's do number 28. So if you look here, you'll see I've got an entire page of work. I presume it took you guys the same thing, but let's take it little bit by little here. Okay, so first thing I do is I draw the picture. So this is the origin. And so I've got one charge over here that's 4 centimeters to the left of the origin. And then my other charge is over here, 4 centimeters to the left, and also up 8 centimeters in the Y direction. So I've got my 3 charges here. And I know these 2 distances, so I can use Pythagorean theorem to figure out what my third distance is. So now I know all 3 of the distances. Okay, and I can easily figure out what that angle is just by taking the inverse tangent of 0.08 over 0.04. So I figure out my angle there is 63 degrees. All right, so now I'm going to, oh, and sig figs, did I do the wrong number of sig figs? Okay, yeah, well, we'll just pretend it's three sig figs. Okay, good. Okay, so now I'm going to use a principle which you need to know the name of because it might be a test question. Okay, the principle of superposition. What the principle of superposition says is that if you've got more than 2 points, what you can do is you can just take them 2 at a time. So let's pretend like this point A here, let's pretend that it's not there. Let's pretend like the only things in the universe are spheres B and C. And so now B is negative and C is also negative. So the fact that I've got 2 like charges, I know the like charges repel. So I can go, so I know immediately that force C is going to feel a force, or sphere C is going to feel a force pushing him to the right. Now there's also going to be an equal force on B, but the question doesn't ask about B. The question only asks about C. So that's all I'm going to worry about here. So I can use Coulomb's law, knowing what is the charge on, oh, okay, so here's Coulomb's constant, don't forget that. So I got the charge on B, I got the charge on C, I've got the distance squared, and so I find out that this charge right here is 5.100 times 10 to the negative 5th. So I figured that out. Okay, so now I pretend like B isn't there, and I pretend like the only charges in the world are A and C. Now A is positive, C is negative, so I know that they're going to be attracted. So I can go ahead and draw this arrow right here. Before I even do the math, I already know it's going to be attracted. Okay, so then I use Coulomb's law again. So I put in the charges, put in the distance, and I had to use Pythagorean theorem to figure out what the distance was. Okay, so now I get this number. So now I know what the two forces are. So the electrostatic part of the problem is finished. So from this point on, it's no longer an electrostatic problem. Now it's just a vector addition problem. And you guys are good at vector addition, right? Okay, well, I certainly hope so. So let's go down and let's see if we're good at vector addition. Okay, so what I've done is I've taken this up here and I've redrawn it down here. So I've got a force to the right, I've got a force up here. This force up here is a funky force. What do we always do with funky forces? We keep calm and we defunkify them. Okay, so over here you can see I've taken my funky force and I've broken it up into its components, right? Okay, so there they are. So now I don't need the funky one anymore because I've got these two components to do the same thing. Okay, so now what do? I add up all of the forces that are in the x direction. So I've got this guy pulling to the right, and I've got this guy pulling to the left. So it's going to be right minus left. So this is the number that I get as my sum of the forces in the x direction. Now in the y direction, I only have one force. So that's easy. So I just, whatever that is, that's going to be my sigma Fy. So now I have my final components of the final answer. Okay, and so this is what they look like. So if this is sphere C, it feels a force pulling it to the right, and it also feels a force adding it up. Now, when I draw the picture to add the vectors, remember, I got to draw it the way that sailors do. I've got to draw the first vector, and then wherever the first vector ended, that's where I start drawing the second vector. Okay, I do not want to just draw a line right over here. Okay, I know it's been a while and some of you have forgotten. So do not just draw a line between connecting these guys up. That's not the way that it works. Do it the way that a sailor would do it. Draw the first vector, and wherever the first vector ends, start drawing the second vector. And this right here, that is our answer. So if we just Pythagorize these guys, then it'll give us 4.83 times 10 to the negative 5. And then if we just take the inverse tangent of these guys, it'll give us 45.7. So this would definitely be the kind of problem that I would put on part 2 of the test, not on part 1. And because there are so many steps involved, there's a high probability that somewhere along the way you're going to make a silly little mistake and you're going to get the wrong answer. But as long as I can see your work, okay, as long as you show me all of the steps there, and if I can see that somewhere along the way you just made a silly mistake, but everything else you did right, I will be generous with partial credit, okay? So before I move on, are there any questions about this problem? Which I recognize this was the hardest problem on the test. And you should be prepared for problems like this on the real test. Okay, I'm not seeing any answer or anybody type in any questions. So let me go back. Okay, so that was 28. So Jaron is saying it was confusing. Yeah, I mean, this was a tough problem. So just go back and do it yourself. Remember, the way to learn physics is not to watch somebody else do physics. The only way that you can learn physics is to do it yourself. So I want all of you to go back and redo problem number 28 from scratch by yourself. Don't look at my answers. Just do it by yourself from scratch and then see if you can get the same answer that I got. So DIY physics, yes. Okay, now, so Eleanor wants to know, would I say that the direction is north of east? Well, the problem statement here does not say anything about northeast, southwest, okay? So what I would do in answer to your question there, Eleanor, is I would just draw the picture and I would say, this angle right here is whatever, 45 point, whatever it was, 45.7. I would just draw the picture. Okay, I would not say north of east because the problem statement never said anything about north and east. Okay, so problem number 29. I hope you agree is not anywhere near as difficult as problem number 28 was. So we got a parallel plate capacitor, we got a hole drilled in it. So hopefully you guys recognize, an electron gun. Yes. Okay. So if we want to know the velocity, well, first thing we do is we start with the definition of voltage. We know that the voltage is defined as, I should have put an extra line in there because this is the definition. Voltage is defined as the work divided by the charge. And so if we multiply both sides by charge, we know that the work is equal to Q times delta V. So that is the amount of work that the electric field does on the electron, or let's see, yeah, it's an electron. Yeah, okay. So that's the amount of work that the electric field does on the electron. And so if that's how much work it did, then by definition, that's how much energy it's going to have after that work is over. And since we don't need to worry about gravity here, all we're worried about is velocity. All of that energy is going to be kinetic energy. Okay, and kinetic energy is 1/2 mv squared. Be careful, we got an equation here that has two V's in it, so don't get confused about that. The capital V here is voltage, the lowercase v is velocity. Okay, so Jaron is saying he got a different answer than I did. Well, I have been known to make mistakes. Somebody else want to help me out? Did anybody else? Let me redo the numbers right now. I mean, as you guys know, I have made many mistakes in my life. Okay, so the mass of an electron, 9.11, yep, that's the right number. Okay, so 9.11 times 10 to the negative 31. Okay, the velocity squared, let's see. Okay, so yeah, so velocity is 535, so 535,000. I square that. Okay. Hang on a second here, I forgot to say times. Okay. All right, and then I want to divide that by 2, and I also want to divide it by the charge of the electron, which is 1.6 times 10 to the negative 19. So, Jaron, I'm getting the same answer now that I got before. And I see other people are supporting me as well. Okay, good. So yeah, so Jaron, just go back and check your calculators there. Probably just punched in the wrong number. It's easy to happen. Okay, so we've already talked about that. Okay, and then problem number 30. All I want you to do here is just draw the pictures. Okay, so in this case, the antenna is a little different than what I showed before. What I've got here is I've got a ball up on top, and that ball serves as a reservoir that can hold excess charge. So when we turn on our power supply and the positive charges go rushing up the wire, they have a place that they can go into. They have a little reservoir that will hold them temporarily. Okay, so when the charges go rushing up the wire, we use our right hand rule and we hold the wire and we see what the magnetic field lines look like, okay? And then, and by now you guys realize that if those magnetic field lines are constant, you know, if instead of having a short burst, if we had a constant current going up here, those magnetic field lines would appear and they would stay there. And that would be the end of it, okay? But because we're doing things in short bursts, because we're doing AC, not DC, okay? These magnetic field lines are not constant, they're changing. And so when you have changing magnetic field lines, that creates electric field lines, and those changing electric field lines create magnetic field lines, which create more electric field lines, which create more magnetic field lines, and so forth and so on. And so what we have is an electromagnetic wave. Okay. All right, so let's see, is this the last? Okay, we're 2 more to go and we will be done. And yeah, okay, timing is looking good. We haven't hit an hour yet. Okay, problem number 31 here is just a derivation. And hopefully you guys realize this is one of the easiest derivations we've done all year. We just start with the definition of voltage, work over charge, okay? And we recognize that work is the same thing as force times distance. And then we say, hey, wait a minute, force over charge, that by definition is the electric field. So wherever I have force over charge, I can replace that with E. And so I'm left with delta V equals E times D, okay? So this thing that we got right here, the result of this, that is a true statement. It is not the definition of voltage. Over here on the left, that's the definition. This thing on the right is just a very, very useful formula, which we can derive working from the definition. Okay, and now the very, very last question on the test, the one that I think is probably the second most difficult question on the test, although some of you may argue that this one's a little harder. Okay, so what we've got is we've got an electron gun, okay? Except this time, instead of shooting electrons, we're going to take a different type of atom. We're going to ionize the atom. So we're going to give it one extra electron. So it has more negative charge than it does positive. And so since the difference is only one electron, so the charge on it is going to be the same as the charge of an electron. Okay, and we've hooked it up in our electron gun here. It goes shooting out here. It goes into a region of space where we have magnetic field lines that are going into the board. Okay, now this is a negatively charged particle, so we take I'm using my left hand because it's a negative charge particle. So I point my thumb in the direction that the particle is moving. My fingers, I point into the direction of the magnetic field, which is into the board. Okay, which I guess for you guys, I would have to do it like this for it to be for you. Okay, all right. And so then my palm tells me what direction the force is. Okay, so as it goes in here, there's gonna be a force that pulls it off to the right. Now, when it gets over to here, it's now moving this direction right here. So the force is always gonna be perpendicular to the direction that it's moving. So it's gonna be exactly as if I had a little ball on a string, okay? Or exactly as if I had a planet going around the sun. Okay, it's going to move in a circular orbit here, okay? All right, so if I want to know, so I'm going to need to know how fast the object's going. All right, so I take my delta V is Q over V, which I know that the work then is going to be QV, and I know that however much work I do when I'm accelerating it up here, that's how much kinetic energy it's going to have. So I do a little bit of algebra, and so I can come up with a number for how fast that baby is going to be moving when it comes out of my gun. Okay, so now I put it into this equation down here. I know that the force on it is QVB sine theta. And in this case, the theta is 90 degrees, so I don't have to worry about the sine theta part. I can just do QVB. So I know Q. I didn't know what V was before, but now thanks to all this over here, I do now know it. So I can figure out what the force on it is. Okay. All right, so that's how much force is going to be acting on that particle when it enters the magnetic field. Okay, so next I need to recognize that that force is going to make it move in a circle. So if you're moving in a circle, the acceleration is v squared over r. Okay, so this force that we just calculated is going to equal m times v squared over r. So I do a little bit of algebra there to solve for r. And now it's just plug and chug from this point on. And so I get that the radius of the circle there is 0.027 meters, or 2.7 centimeters if you prefer. Okay, now again, this is the kind of problem where there's a whole lot of places where you could easily make a mistake. So I would certainly do this one on part 2 of the test, not part 1. So as long as I can see that you basically knew what you were doing, okay, that if you got the wrong answer, if I can see that it was just a silly mistake, but for the most part you knew what you're doing, I will be generous with partial credit. Okay. And that's it. We have now come to it. So Yasna is asking, is there an extra credit question on the test? Well, there isn't right now. Do you guys like having extra credit problems on the test? Okay, all right. Okay. Oh, yeah. Okay, well, in that case, yeah, I'll put an extra credit problem on the test for you. Okay, well, I think we're done. So Jaren is wanting to know if we have a secret word for the day. Yeah, I guess we should do that. Anybody want to suggest a secret word? Okay, so Emmanuel, suggest it fast. Okay, so Emmanuel, I'll give you 5 seconds to type in your secret word. Okay, okay, there you go. Zawarudo. Oh my goodness. Okay, now I didn't bring my Sharpie here. So let's see. Let's go with Emmanuel's. Let's see, I didn't bring my Sharpie. So can I, here, maybe I can write it on here. Okay, so Za, that's an A, it doesn't look like it. Okay, and then capital W, and boy, yeah, it's really hard writing like this. That's an R, and then U, D, O. Okay, wow. I cannot write well using a mouse. Okay, somebody wrote a smiley face, so I guess it couldn't be too bad. Okay, so Emmanuel, is that a word that has any meaning, or is that just a total gibberish word? So Maddie wants to know what part of the test the extra credit will be on. It would definitely be on part 2, because I do want it to be, you guys are having a little too much fun here with the scribbling there. Maybe I'd better quickly turn off the scribbling before somebody writes something on the board that they shouldn't. Okay, so disable annotation. Okay, good. All right, so you guys can't scribble anymore. So Emmanuel, oh, okay. Emmanuel says that it means the world. What language is that in? Okay. All right, so anyway, so Ellie is asking, will there be a quiz on this class? I don't know. What do you guys think? Do you want to have a quiz on it, or you want to just skip the quiz this time? So Yazan wants to go back to question number 20. Okay, so Yazan, I'll do that. It looks like we have overwhelming, everybody wants to do skipping of the quiz. Okay, so I'll skip the quiz today. So Zawa Rudo, keep that one, we'll put that one on later. Okay, so oops, oh my, oh hey, look. Oh, when I touch the screen here, it lets me write on the screen. Oh, I didn't need to use the mouse, I could use my finger. Isn't that cool? I didn't know that. Okay, so let's turn off annotation. Oh, and let's, now how to get rid of all those annotations. Let's see. How do I get rid of annotation? We'll just leave it on there for now. Okay, so Yazan, you wanted to go back to number 20. Okay. And so your question is probably the direction. Okay, so in order to get the direction, use the right-hand rule. Even though the angle is not 90 degrees, you can still use the right-hand rule. It still works. So if your thumb, instead of being off like this, if your thumb is still like this, the palm is still going to point the direction of the force. Okay. So does that answer your question there, Yazan?
No, I was just wondering for the B, like how do you know it's pointed to the right?
How do I know it's what?
Pointed towards the right.
To the right? Okay. Well, okay, so the particle is a negative charge, so that means I'm going to use my left hand, not my right hand. Okay, it's moving in a direction that's 28 degrees east of north. So I'm going to take my thumb and I'm going to put it, so my thumb is going to be 28 degrees east of north. Okay, and so then so east of north. So let's see, so where I am, that's north that way, that's east. So my thumb is going to point that way. My fingers are going to point, let's see, the problem says that it goes to the east. Okay, so when I hold my hand here, my thumb is not pointing straight north, but it's a little bit to the east of north. My fingers are pointing east. My palm is pointing upward, okay? So even though the angle here is not 90 degrees, even though the angle is something less than 90 degrees, you can still use the right hand rule. Or in this case, since because it's a negative charge, I'm using my left hand, but it still works. Oh, okay, so Jaron, apparently Jaron must have been Googling things while we were talking. So he's saying Zawarudo Tokiwa Tomarei. It says the world stopped time. It's said by a vampire who can stop time. Um, so Sarah wants to know if it's Japanese. I mean, it kind of sort of sounds Japanese, but those are none of those. Oh, warudo. Yeah, that's Tokiwa. Oh, yeah, that is Japanese. Yeah, okay. Yeah, warudo. I love it. In Japan, what they do is they take an English word, and when they put it into Japanese, they pronounce it. They take world and they put it into warudo. It's yeah, okay. Yeah, it is Japanese. Okay, I think we're done. And it's been exactly 1 hour since we started, and I like to keep these things to 1 hour. So unless I hear any complaints, I am going to stop the recording and end the class. So going once. So Stardust Crusaders, the third part of JoJo. Okay, you guys are really into this anime here. Okay, going once. Going twice. Okay, I'm going to stop the recording.